We're going to take a look at orbits and the different kinds of orbits. So have your engineering notebook out as always, and I'm going to explain the orbits that you see in front of you. So an orbit is just a closed path around which a planet or satellite travels. Johannes Kepler discovered in 1600 that planets orbit in ellipses, not circles, which is really an amazing thing that he figured that out, which we talked about already. You need to note also satellites, which are either natural or human-made. Natural meaning like asteroids, things like that. Also orbit Earth in elliptical patterns, along with planets. And elliptical orbits remain fixed in space, and Earth spins under that fixed satellite. So the satellite's orbit is always this, but the Earth is spinning underneath that. And so it sort of gives the impression that the satellite is the one that's kind of changing where it is around the Earth, but that is in fact not the case. So we have all sorts of orbits. If you take a look at this, you can see the low Earth orbit, or LEO, the polar orbit, which is the white one on there, that vertical one. It's not called a PO. It's just polar orbit. The medium Earth orbit, or MEO, highly elliptical orbit, or HEO, and geostationary orbit, or GEO. There's also this Minaya orbit, or MALI here, and that is sort of the highly elliptical variety, a Minaya orbit, but there's a specific reason for that one, which we'll get to. So first is low Earth orbit. This is really cool. There's several, it's relatively close to Earth, and there are several hundreds of objects in low Earth orbit. This is characterized by a short orbital period, so really important. It's roughly 90 minutes. For those objects in low Earth orbit, again, they can travel around one entire orbital period in 90 minutes. They make many revolutions per day. In fact, they make exactly however many revolutions 90 minutes happens in a day. And because of that, they have a limited swath area, the area that a satellite can see. All staff space missions except lunar missions have been to LEO. We do not go outside LEO ever unless we've gone to the moon. The space station is in low Earth orbit, so we are incredibly close to Earth with respect to the solar system and the distance from here to the moon, even when we're at the space station. Many Earth observing satellites are LEO orbits also because they're so close. So next is a geostationary orbit. Its name, geostationary, means it just stays in one spot with respect to the Earth. So if you watch this image, you're kind of seeing that this satellite, as it's spinning around the Earth, it's always pointing at the exact same location. So you achieve this by placing the satellite at an exact specific altitude where the orbital period is exactly 1 day. Remember, low Earth orbit is 90 minutes, but as we get further and further away, then that orbital period grows and grows and grows. It takes longer and longer to complete an orbit until we get to that perfect distance, which is 22,300 miles, where one orbit is 1 day, and that means you're always pointing at the same place. The angle of inclination is exactly zero, not usually, it's exactly zero, because if you're a little bit higher, if you have a different sort of angle of inclination, you're not really going to be geostationary anymore, because you're not pointing in one spot. You would be seeing different parts of the Earth. So that is geostationary, is inclination of zero. There is only one altitude above Earth with an orbital period of 24 hours. So all geostationary orbits, and this is looking kind of at the pole, you can see right here. I was looking at Antarctica. All geostationary orbits are in a ring around the Earth. So this ring is called the geostationary belt. And it is a limited resource. You could see, obviously the satellites are not this large. These would be giant satellites, like, the size of the state of Alaska, right, with respect to this planet. But there is a limited number of satellites you could have. We have not really come close to that, but when you think about the amount of safe distance, that safe space between satellites, then you can recognize that it could become an issue. And maybe if you want to have a lot of satellites pointing over the United States, for example, if you are Dish Network or Comcast or whatever you are, if you want to have these satellites that are giving you constant communications, then that can be a problem because there is a limited number of space, especially when you're talking over one continent versus the entire planet. We don't really need all that many straight over the Pacific Ocean because of communications, things like that aren't really significant. So a short lesson on urban navigation. How can you tell what direction is south if you're lost in the middle of urban United States with no compass or GPS receiver? So this is kind of tricky. Your hint on this is a little riddle. Your hint on this is thinking about Dish Network. That's your hint. All right, so pause this and see if you can come up with the answer. And it's sort of blurred in here, but if you look for a building or house with a TV satellite dish, geostationary satellites can only hover above the equator, so they are always going to be south of us. So all northern hemisphere dishes are communicating with satellites that are south. I know it's cut off in there, but they're all going to be pointing to the south to be able to connect with that satellite. Pretty cool, huh? A Minaya or Mali orbit is another one we're going to look at. Geostationary satellites for Russian communications pose severe challenges since a majority of its landmass is far too north for geostationary belt satellites to see. We are way, way, way too far north here. So it doesn't work to just have a geostationary satellite. So the solution was to create a type of orbit called a Minaya orbit, and it allows long-term communications over northern Russia landmass. So here's how they do it. This is sort of cool here. As you are watching this, it says Minaya ground trace differs from most conventional ground trace images. The image below clearly illustrates satellites' hang time over Russia. As you're watching this, you're seeing that when it's over Russia, that ground trace shows that it's there for a long period of time, because in that orbit, when it's way, way, way up there, it's always sort of pointing at the north. So that's why it appears on the ground trace to be moving slow. Now, another thing to note is that as you get closer and closer to the Earth, the speed of the satellite increases. So it quickly whips around into the southern hemisphere, and then it's back into the northern hemisphere again where it can see it. So two satellites could, in this exact same orbit, could cover, that the trace over Russia for most of the time. What I find kind of interesting is that the other location that it's over is the United States. So another orbit is a polar orbit. The polar orbit has a 90-degree inclination. Satellites will eventually pass over all the Earth. If it just continues to do this, as the Earth is spinning around it, it's going to be able to map the entire planet. So polar satellites, polar orbit satellites can gather information about the entire Earth. They are awesome for weather satellites because you have a great snapshot of everything. As long as you have enough of them, then you can get snapshots all over the Earth. But you look at where they all are intersecting, somewhere around here. Now, they don't all have to go directly over the polar north and polar south. Right over the north and south, if they had a slight angle of inclination given to them, they would have a greater chance of missing. But that's why when we looked at that ESA video, they showed the greatest risk of collision is always near the poles. So Constellation's single satellites are often insufficient to perform a mission. If you think about the weather satellite, just one of them isn't going to help. You need a lot of them. So groups of satellites in various orbits work together to accomplish a mission, and the grouping is called a constellation. Great vocab word. A grouping of satellites like GPS. Now that you know the basics, use your new understanding of orbits to answer these questions. So critical thinking questions, really give this a shot and see if you can answer. If Norway wanted to obtain satellite imagery for all of its major urban areas, think Norway, where it is in the way northern hemisphere, what type of orbit would be appropriate? And second, could researchers at McMurdo Station in Antarctica use geostationary satellites for communications? So thinking about the Norway one, if you wanted to obtain satellite imagery, you might do some sort of a Minaya orbit or a highly elliptical type orbit so that you are way up in the northern hemisphere a long period of time. Imagery of its major urban areas, you could do polar orbits and just have the Earth pass underneath it. That would be another option. So number two, could they use geostationary? Not solely, they could not. They could bounce information off geostationary satellites. So if you had polar satellites you had enough of them, that was always one that was available, it may be able to send a signal from there to one of the geostationary satellites and then out from there, depending on where you needed to go. So it could use it, but probably not entirely, because geostationary is not going to be able to see McMurdo Station and the South Pole. All right, answer these questions. Planets orbit in circles, true or false? Name 3 types of orbits. A geostationary satellite can orbit around the moon. You may need to pause that one if you want to think about that one. How long is the orbit period of a geostationary satellite? And Minaya orbits are commonly used to view Russia. A satellite in an equatorial orbit or inclination of 0 will eventually pass over the entire Earth. All right, let's take a look. So planets orbit in circles. False. They orbit in ellipses. 3 types of orbits: polar, geostationary, highly elliptical, low Earth, Minaya. There's a bunch of them. A geostationary satellite can orbit around the moon. False. A geostationary satellite cannot orbit around the moon. And here we've listed these out. How long is the orbit period of a geostationary satellite? 24 hours. Same as the Earth spinning. Minaya orbits are commonly used to view Russia. True. And a satellite equatorial orbit of 0 will eventually pass the entire Earth. That is false. You need a polar orbit. It's really just going to see the equator, and that's it. So that is it for our introduction into orbits.